So even though this chapter is on data, we are also going through various processes which are looked at with data, or processes that require data to better understand, especially in terms of how they are changing. So keep that in mind, and also keep in mind how complicated things are in terms of covering globally all the data we need to interpret the changes that are occurring. I already said once, I think at least a couple of times, that we are trapping more energy into the Earth system, climate system, when we increase greenhouse gases. That energy is going to be distributed into evaporating the ocean, melting the glaciers, warming the atmosphere, and warming the ocean as well, because ocean is deep and has a high heat capacity, and it covers so much of the Earth's surface, 70%. It takes up almost all of the energy. So 93.4% of the excess energy from global warming goes into the ocean. 2.3% remains in the atmosphere, which appears as the global warming that we have been looking at with its patterns, because the dynamics moves the heat around in the atmosphere as well as in the ocean. Continents keep 2.1% approximately. Glaciers and ice caps are taking up 0.9%. So glaciers can actually warm as well as melt. Okay, it's not just that they are melting all the time. Arctic sea ice 0.8%, which goes into melting and reducing the extent. Greenland ice sheet, Antarctic ice sheet. Okay, so keep that in mind. And for doing these calculations, we need data. And each of these calculations have uncertainties because of the lack of complete coverage in space and time, as we mention again and again. We will look at the coverage of space and time in a little bit. So Earth's energy imbalance then can be looked at in terms of the incoming solar radiation and outgoing long wave or infrared radiation. So here is the outgoing radiation. There is an imbalance of about half a watt per meter squared with a large range because there are uncertainties in the data, so you have to have global data to make global energy balance and so on. So this is kind of the excess energy that is being trapped. So if you think of it in terms of how much CO2 reduction is needed to balance out this excess energy, then that's about 57 plus or minus 8 parts per million by volume. And this is showing just the numbers of where the energy is going, again, as we already saw. So you can see the numbers here are different because this is just comparing two periods, 1971 to 2018 with the baseline of 2010 to 2018. So just again re-emphasizing that some accumulates in the atmosphere. There is a total amount of heat gain because of this global warming. Land is taking up certain percentage. Ocean is taking up most of it. Cryosphere is taking quite a bit of it as well. So the relative impacts can also be understood, because if you melt the cryosphere, you change the albedo, you absorb more energy. So this ice albedo feedback is a very, very critical feedback in the Earth system and has played a big role throughout Earth's history in terms of the growth of the ice age, retreat of the ice age, growth of glaciers, retreat of glaciers, and so on and so forth. So we also have to understand the consequences of each of the energy partition here. If we look at sea level trends in millimeter per year, this is I think for some period 1960s to the present or so, it doesn't matter. We are mostly trying to make points about the data. So sea level, here you can see again the dynamics of the temperature change that we saw obviously also affects the dynamics of circulation change, heat uptake by the ocean, and sea level. So you can imagine a warmer ocean is going to expand and have a higher volume, so sea level is going to rise. And of course tide gauges that have been around for several centuries in many places are one of the best sources of sea level data. But when you go away from the islands and land into the regions, You need other ways to estimate sea level change. And remember, the glacier melt is going to increase sea level as well as the warming. So the sea level change in the ocean is related not just to temperature but density change. So there is a salinity involved as well. So there are thermosteric changes, so temperature changes and salinity changes that together produce the observed sea level change. So there are satellites which can measure sea level. Amazing. They are at some 1400 kilometers up. They send a laser and measure the time of travel, and they can tell you centimeter level change in sea level. So they have to remove the tides, the waves, and the atmospheric changes in humidity and water and clouds and so on, and a lot of calculations are done to derive the tiny bit of sea level that changes over a long. You can see this is millimeter per year, so we are changing by a little bit, but it's very critical because obviously sea level rise along with the warming and changes in cyclones are going to change flooding and inundation and storm surge and many other things as well. So sea level is a very important measure of global warming as well, and a lot of data is being collected in situ and from satellites. So here is an estimate of 0 to 2000 meter global ocean heat content starting in the 1960s. So I suspect this is the same period here. I'm not being very careful because it's not that critical for the points we want to make here about data. So heat content in 10 to the 22 joules over this period. You can see that this baseline of 0 is for defined for some period here. 1960 to 2005 is the baseline. I think you can check it. Okay, so we were below, but we have now increased steadily, and there is 3 month. So there are satellite data being added during more recent periods. So the coverage or the amount of data is increasing as well. Yearly average through 2020 here, and pentadal average, 5-day average, or maybe it's 5-year average from 2016 to 2020. So just like temperature is increasing and the temperature rise is accelerating, sea level rise is also accelerating, and there is a pattern. It's not uniformly rising like a bathtub. So coverage, sampling is very critical. So global mean sea level from altimetry, so that's a satellite that is shooting lasers and measuring the changes, and tide gauges, and there is a range of uncertainty there in these shades. So global mean sea level rise from 1880 to the present, you can see that's well over a meter, well over a couple of meters. Groundwater changes, contributions for 2005 to 2015 for sea level change. So relatively speaking, sea level can change even if the land sinks and the ocean remains the same, or land rises and the ocean remains the same. So things like groundwater change and glacier change, etc., contribute in different ways. Groundwater change will raise the ground because you are withdrawing water, using it and sending it off to the ocean eventually. So Greenland ice melt is adding, Antarctic ice, glaciers, other glaciers, mountain glaciers, and thermal expansion is adding 40%. Okay, so that's a critical calculation we have to make as well. So the pie chart shows the relative contributions from melting of land ice, 1.8 millimeter per year. I won't read the uncertainties. Thermal expansion, 1.4 millimeter per year. And groundwater pumping, 0.4 millimeter per year during 2005 to 2015. So during this period, the melting of land ice is contributing more than the thermal expansion. Of course, thermal expansion is then happening over a long period. So the total rate of sea level rise during this period is 3.6 millimeter per year, larger than during the earlier which is larger than during the earlier periods. Okay, so I will leave the ocean part here. There are many details we are not covering because we are focused on climate science. We'll look a little bit at carbon cycle next, but ocean ecosystems, corals, ocean acidification, the exchanges with land, so eutrophication, harmful algal blooms, pathogens, viruses, disease pressure for the marine ecosystem, all sorts of things change. Technically, you want to have data on everything. So slowly we are beginning to understand more and more of the climate change or even climate variability and the impact. So the plans to collect more and more data grow as the drone technology, autonomous vehicles, satellite technology, and gliders and so on increase, robots, etc., and ways to use ocean energy. So you can use gravity to go down, pull down an instrument, and use the thermal energy to come back up. So there are all kinds of very interesting innovations on collecting data. So if you are interested in the technology side, you can read up on those as well. So amount of data continues to grow, but we still have a long way to go in terms of what we need to actually monitor, understand, and predict and project the changes and the impacts. I'm resuming this lecture because I need to add another important point. The ocean, which is several kilometers deep on average, doesn't just get heat from the global warming by diffusion. That's a very slow process. There are specific places, like remember in the Greenland, Iceland, Norwegian Sea, when we looked at the global warming trend, we said there is either no warming or even a cooling happening. That's a place where water sinks like a rock to the bottom. There are also places in the Ross Sea and Weddell Sea in the southern ocean of Antarctica where waters sink to the bottom. So when they sink, they take not only the heat with them but also other greenhouse gases, oxygen, and so on and so forth. And there are other places where ocean communicates from below the surface to the surface where heat can go down faster. That's called the advection process, where water takes the heat and actually takes it with it. It's like air parcel that is rising from your heater going up and taking the heat with it and circulating in the room. Okay, so convection as opposed to diffusion by molecular processes or conduction by molecular processes. So this gives us additional problem in the sense that the ocean is warming faster near the surface, of course, because of exchanges with the atmosphere. There are dynamic processes happening there called AFC interactions, but it's warming slowly as you go deeper and deeper, and it's a concern that the heating is reaching greater and greater depths over time. So here we are looking at ocean globally again, 0 to 300 meters, and so we are looking at the ocean and land here with more recent data here, but just focus on ocean for a second. So the light blue line here is 0 to 300 meter, which is increasing. There is 0 to 700 meter, which is also increasing over time. Ocean below 2000 still remains smaller, so 700 to 2000 meter also remains smaller than the upper ocean, but you can see that their heating is increasing with time. So more and more heat is making it to the deeper ocean. So and there is the land warming and ice energy uptake and the uncertainties that remain and so on. But uncertainties means the data sampling issues. For example, deep ocean warming, monitoring it across the globe is not very easy. We use whatever data we can, so we can see that several time scales are involved here. So the deep warming ocean below 2000 is only shown here from the mid 1990s onwards, whereas the 700 to 2000 and other regions of the ocean are being shown from the 1960s onwards. So the coverage is increasing, but ocean remains incredibly difficult, especially far away from islands and lands and continents, to collect data. but this is a critical need for data in terms of what we need to monitor where all the energy is going. We need to have a very good handle on how much excess energy is being trapped by the increase in greenhouse gases and where that energy is going, because the consequences and the future evolution of warming in the atmosphere. When we talk about global warming, we're typically talking about warming in the atmosphere, but the ocean warming is storing a tremendous amount of energy that obviously has a consequence for a long time. So I wanted to just add that before we move to carbon cycle data. Okay, let me stop this here.